In heat transfer at a boundary within a fluid, the Nusselt number is the ratio of convective to conductive heat transfer across the boundary. In this context, convection includes both advection and diffusion. Named after Wilhelm Nusselt, it is a dimensionless number. The conductive component is measured under the same conditions as the heat convection, but with a stagnant fluid. A similar non-dimensional parameter is Biot number, with the difference that the thermal conductivity is of the solid body and not the fluid. A Nusselt number close to 1, namely convection and conduction of similar magnitude, is characteristic of slug flow, or laminar flow. A larger Nusselt number corresponds to more active convection, with turbulent flow typically in the 100–1000 range. The convection and conduction heat flows are parallel to each other and to the surface normal of the boundary surface, and are all perpendicular to the mean fluid flow in the simple case, where h is the convective heat transfer coefficient of the flow, L is the characteristic length, K is the thermal conductivity of the fluid. Selection of the characteristic length should be in the direction of growth of the boundary layer. Some examples of characteristic length are the outer diameter of a cylinder in crossflow, the length of a vertical plate undergoing natural convection, or the diameter of a sphere. For complex shapes, the length may be defined as the volume of the fluid body divided by the surface area. The thermal conductivity of the fluid is typically evaluated at the film temperature, which for engineering purposes may be calculated as the mean average of the bulk fluid temperature and wall surface temperature. In contrast to the definition given above, known as average Nusselt number, local Nusselt number is defined by taking the length to be the distance from the surface boundary to the local point of interest. The mean, or average, number is obtained by integrating the expression over the range of interest, such as the mass transfer analog of the Nusselt number is the Sherwood number. Introduction. An understanding of convection boundary layers is necessary to understanding convective heat transfer between a surface and a fluid flowing past it. A thermal boundary layer develops if the fluid free stream temperature and the surface temperatures differ. A temperature profile exists due to the energy exchange resulting from this temperature difference. The heat transfer rate can then be written as, and because heat transfer at the surface is by conduction, these two terms are equal, thus rearranging, making it dimensionless by multiplying by representative length L. The right-hand side is now the ratio of the temperature gradient at the surface to the reference temperature gradient, while the left-hand side is similar to the Biot modulus. Derivation. The Nusselt number may be obtained by a non-dimensional analysis of Fourier's law since it is equal to the dimensionless temperature gradient at the surface, where Q is the heat flux, K is the constant thermal conductivity and T the fluid temperature. Indeed, if and we arrive at then we define so the equation becomes by integrating over the surface of the body, where empirical correlations. Typically, for free convection, the average Nusselt number is expressed as a function of the Rayleigh number and the Prandtl number, written as otherwise. For forced convection, the Nusselt number is generally a function of the Reynolds number and the Prandtl number, or empirical correlations for a wide variety of geometries are available that express the Nusselt number in the aforementioned forms. Free convection at a vertical wall cited as coming from Churchwell and Hugh. Free convection from horizontal plates if the characteristic length is defined where is the surface area of the plate and is its perimeter. Then for the top surface of a hot object in a colder environment or bottom surface of a cold object in a hotter environment, and for the bottom surface of a hot object in a colder environment or top surface of a cold object in a hotter environment. Forced convection on flat plate in laminar flow. The local Nusselt number for laminar flow over a flat plate is given by flat plate in laminar flow. The average Nusselt number for laminar flow over a flat plate is given by forced convection in turbulent pipe flow. Nolinsky's correlation for turbulent flow in tubes. where F is the Darcy friction factor that can either be obtained from the Moody chart or for smooth tubes from correlation developed by Pachukov. The Nolinsky correlation is valid for Dittis-Boelter equation. The Dittis-Boelter equation is an explicit function for calculating the Nusselt number. It is easy to solve but is less accurate when there is a large temperature difference across the fluid. It is tailored to smooth tubes, so use for rough tubes is cautioned. The Dittis-Boelter equation is where is the inside diameter of the circular duct is the Prandtl number for heating of the fluid, and for cooling of the fluid. The Dittis-Boelter equation is valid. For example, the Dittis-Boelter equation is a good approximation where temperature differences between bulk fluid and heat transfer surface are minimal, avoiding equation complexity and iterative solving. Taking water with a bulk fluid, average temperature of 20 degrees Celsius, viscosity 10.07 times 10⁻⁴ pascals S, and a heat transfer surface temperature of 40 degrees Celsius, making a significant difference to the Nusselt number and the heat transfer coefficient. C-to-Tate correlation. The C-to-Tate correlation for turbulent flow is an implicit function, as it analyzes the system as a nonlinear boundary value problem. The C-to-Tate result can be more accurate as it takes into account the change in viscosity due to temperature change between the bulk fluid, average temperature, and the heat transfer surface temperature, respectively. The C-to-Tate correlation is normally solved by an iterative process, as the viscosity factor will change as the Nusselt number changes. Where is the fluid viscosity at the bulk fluid temperature is the fluid viscosity at the heat transfer boundary surface temperature. The C-to-Tate correlation is valid for forced convection in fully developed laminar pipe flow. For fully developed internal laminar flow, the Nusselt numbers are constant valued. The values depend on the hydraulic diameter. For internal flow, where